For our second talk today, we have Yutao Liu from the University of Washington, who will tell us about the generalized Tate diagram and slice spectral sequences.
All right, thanks for inviting me. So today I will talk, I'm going to read the topic again, the generalized Tate diagram and the slice spectral sequence. It is a joint project with Vanishing and Guoqi. I'd like to start it with the generalized Tate diagram. Well, let's begin with the Tate diagram. Greenlees and May introduced the following Tate diagram for any G spectrum X, as you can see. Here, tilde EG is the cohabit of a special map from EG plus to S naught. One observation of this diagram is the right square here is in fact a pullback square, which we also call the Tate square. The Tate diagram is a quite powerful tool in equivariant homotopy theory, since if we take the G fixed point of the diagram, then here is what you will get. As you can see, this diagram gives relations among different equivariant constructions associated with X. The middle one, X to the G, is the genuine fixed point of X, where X with lower Hg is the homotopy orbit, where X with upper Hg is the homotopy fixed point. The right bottom corner is the Tate construction. The fixed group of tilde Eg smashed with X is somehow related to the geometric fixed point. In particular, if the order of G is a prime number, then it is the geometric fixed point. The reason why the Tate diagram is powerful is if you want to compute X, then you can first decompose X into smaller pieces. You can analyze them individually, and you can use a diagram to glue them back. In general, if F is a family of subgroups of G, then we have the following generalized Tate diagram, where you replace EG by EF. Here, EF is a special G space, which is characterized by the property by its fixed point subspaces, which is either contractible or empty, depending on if the group is counted in F. In particular, if F is the family of only the trivial subgroup, then the space EF agrees with EG, and we get the classical Tate diagram. The initial idea of our project is to apply the generalized Tate diagram not on a space, but on spatial sequences. If you replace the space X by a filtered G spectrum Px, where P bullet X, then here is how the generalized Tate diagram will become. As you can see, it is a diagram of filtered G spectra. So when taking the underlying spectral spaces, you will get a diagram among different equivariant spectral sequences. Our goal is to use this diagram to analyze the equivariant slice filtration of MUG modules. Well, I will explain what they are right now. Well, the story of the MUG modules, the story for both traces way back to the covariant invariant 1 problem. In 2009, Hill-Hopkins-Ravenel proved that the covariant invariant elements theta j do not exist when the degree is at least 7. In their proof, they invented the equivariant slice filtration and used it to study the inverse MUC8, which is a C8 equivariant spectrum. And here is how you can construct such spectrum. You can begin with the non-equivariant MU, which can be upgraded to a C2 spectrum, which we call the MUR, by using the complex conjugation as the C2 action. It was studied by multiple people by Landweber, Araki, Fuji, and Hu and Chris with different methods. When we localize at 2, the Queen idempotent also has a C2 lift, and here is how we can construct BPR. Then we can take the norms of either MUR and BPR, so we can construct MU or BP as a C2 to the N equivariant spectrum. We can also construct the quotient modules, which is the equivariant analog of either MUM or BPM. Then, if we invert a suitably chosen class, we will have a periodic version of the quotient of BP C2 to the N. There are several special examples about such construction. Well, for example, if you consider the periodic version of VPR1, then you recover a TS real K theory. In general, if you consider the periodic version of VPR to the N, then you recover the real Johnson-Wilson theory. And these quotients are quite important for computations in chromatic homotopy series. Another motivation why such special spectra are quite important is given by Han and Shi, where they showed that there exists a C2 equivariant orientation from MUR to the molar E theory, and then they use them to compute the C2 fixed point of the molar E theory. Later, Meier-Shi, Hill, Shi, and Zeng, they show that the periodic version of the quotient of VP C2 to the n gives a C2 to the n equivariant model for the molar E theory. And here is a large graph which shows how this system works. If you take different quotients of VPC to the n and you take their periodic construction, then they will provide perfect models for different molar E series with C2 to the n actions. Then the slice special sequence comes into our story since it's quite computable when we apply it on these special periodic quotient BP modules, which enables us to compute the homotopy of the fixed points of the molar E series. Now I'm going to introduce the slice special sequence. The slice filtration, P bullet X, is a generalized Poisson-Nikodym filtration, but we replace the non-equivariant spheres, so S to the n, by these equivariant spheres. As you can see, it comes from the regular representations of H, and then you induce it to make it into a G space. Then the universal map from X to each Pnx, it nullifies all maps from higher spheres, from these spheres with degrees greater than n. The slice special sequence is the special sequence associated with this special filtration. It is an ROG graded special sequence if you take the ROG graded homotopy. The slice special sequence is quite powerful for the types of spectra we talked before, since they have quite a nice slice, where the slice is the fiber of the adjacent maps on the slice tower. The odd slices are always trivial, while the even slices are always wedge sums of suspensions of Hz, the Ellenberg-MacLean spectrum with constant z coefficients, which means we can compute the E2 page by the homotopy of Hz, by part of the homotopy of Hz, which are completely computable. Here are some examples. Well, the first example is the slice special sequence of this periodic BPR1, which is the same as a TS real K theory. It is a model for the C2 fixed point of the molar E theory E1. Well, one interesting thing for this computation is it also implies the Bott periodicity. Since if you trace all the surviving point on this graph, so the box is a copy of Z, the black point is a copy of Z2. You can see the Z2, Z2, Z, 0, Z, and well, you can see the Z2, Z2, 0, Z, and the 0, 0, 0, Z if you go from degree 1 to degree 8. And here is a more complicated example. Well, if you can see the graph clearly. So here is the spectral sequence for the periodic for the inverse of BPC41, which is a model for the C4 fixed point of the molar E theory E2. There are several important observations of this graph. For example, you can see the whole spectral sequence is divided into two cones, and you can divide each cone into different regions. Well, observation 1, the slice spectral sequence can be divided into two cones. We call the right one to be the positive cone, and we call the left one to be the negative cone. If you go back to this graph, as you can see, yeah, there are two conical regions. And also for our previous example on KR, it is also two cones, just more simple than the other example. Moreover, we can divide each cone. We can stratify it into different regions. In this example, as you can see, each of the two cones are divided by two different regions, where each of the two regions have completely different behaviors on the differentials. You can see on the upper region, it seems to be quite symmetric about this length phi differential, but in the lower region, it seems different kinds of differentials are just mixed together. And moreover, there seems to be a kind of symmetry between the two cones. Well, it's quite obvious from this graph, since the negative cone seems to be just rotate the positive cone by 180 degrees. On the previous example, it's not quite clear, but there's also some kinds of symmetry between the two cones. You can see the differentials are quite similar to each other. Well, our goal is to systematically study the positive cone, the negative cone, and also their relations. There are some kinds of periodicity and symmetry phenomena between the two cones. And then we can use these structures to do more computations at higher heights. So we can compute more slice spectral sequence and obtain more information on different Morova E series. The key technique in our theory is the following generalized Tate diagram of a slice spectral sequence. So I'm going to state our main results. Well, so first, we can obtain a kind of stratification on both cones. Well, by applying the generalized Tate diagram, it provides us stratification on both the positive cone and the negative cone of the slice spectral sequence, which divides both cones into different regions. And further, we can detect them with Tate spectral sequence, which is after we divide them into different regions, we can study the individual regions in the slice spectral sequence by the isomorphism with the corresponding generalized Tate spectral sequences. As an application, this will give us transchromatic results which relates the homotopy of different Morova E series. And moreover, there are several periodicity and symmetry results in the slice spectral sequence which are kind of hidden just on the spectral sequence, but they will be revealed if we compare their relation with the generalized Tate spectral sequence. And these structures are quite powerful when doing computations. I will give a concrete example at the end of my talk, and you will see how powerful to apply the structures to compute the slice spectral sequence. I'd like to begin with the first result, the stratification of the slice spectral sequence. I'm going to give you a graph, and then I will explain different elements on this graph. Well, as you can see, the middle of this graph is the slice tower, which gives you the slice spectral sequence. The two halves of the graph represents both cones. The right one is the positive cone, the left one is the negative cone. And here, these special towers, on the right half, you have tilde EG smashed with the slice tower, and the different tilde EF smashed with the slice tower. This provides a stratification on the positive cone. As you can see, if you focus on the region over a line with slice 0, 1, 3, and so on, then you can detect those regions by these different towers. A similar thing happens on the negative cone, but here you choose your detecting tower by the mapping space from tilde EF to the slice tower. We call this diagram to be a butterfly diagram, and here is the reason. As you can see, it looks like a butterfly. I'm going to explain more details so you will understand better how this diagram behaves in the slice spectral sequence. So we begin with G as C2 to the N, and we choose Fi to be the family of all subgroups stop at C2 to the I. So first, we can apply the smashing with tilde EF to the slice tower, which implies a spectral sequence we call the localized slice spectral sequence. Choose different I, you can obtain a stratification of the towers, since you have maps among different tilde EF. Then each localized slice spectral sequence preserves part of the information in the positive cone of the slice spectral sequence. This theory was studied by Meier-Shi and Zeng before. On the negative cone, we have a similar but slightly more complicated story. So if you want to get a stratification of the negative cone, here is what you can do. We look at the vertical fibers of the Tate square. So the bottom square here is the Tate square in the generalized Tate diagram. We take the fiber of them. Since it is a pullback square, the two fibers are the same as each other, which are the mapping spectrum from tilde EF to the slice tower. And we call this mapping spectrum from tilde EF to be the co-geometric construction. Then taking different eye, you can obtain a sequence on the opposite direction. You have maps from different mapping spectrum from tilde EI to the slice tower. Now, after we have both filtration, we can explain how they represent different regions on the slice spectral sequence. We have the following slice recovery theorem. It is the combination between the theorem by Meier-Shi-Zeng and also by us. Well, in the positive cone, the map from the slice tower to the localized slice tower induces an isomorphism of spectral sequences above a line of slope 2 to the I minus 1. In the negative cone, you have the opposite direction. The map from the co-geometric construction to the slice tower induces an isomorphism of spectral sequences below a line with slope 2 to the I minus 1. Well, I'm going to give you several graphs to explain this theorem. So here is one example. It is a graph on the positive cone. So it is the slice spectral sequence of BPC41, the left graph. For the right graph, it is the localized slice spectral sequence for the family F1. As you can see, they are isomorphic above the line with slope 1. So the line in the middle has slope 1. You can see everything behaves the same above it. Well, below the line, there might be some differences between the two graphs. And here is another example. If I replace F1 by F0, now the two graphs, the slice versus the localized slice, they are isomorphic above a line above the line with slope 0, which is the horizontal axis. So everything in the first quadrant are the same as each other, but as you can see, the second graph has something more below the horizontal line, which does not appear in the slice spectral sequence. Well, one application for this slice recovery theorem is, since when we construct both the localized slice or the co-geometric construction, both of them come from the geometric fixed point or the dual of the geometric fixed point. So we can relate them to the spectral sequences which are acted on by quotient groups of G. And we have the following transchromatic isomorphism theorem. It is also a combination between the theorem by Meier-Shi-Zeng and also by us. Well, if you rescale the length of the differentials by changing dr to d to the r minus 1, then different regions, so you have two regions, in the slice spectral sequence can be related to the slice spectral sequence of a spectra with a smaller acting group, C2 to the n minus 1. Here is a graph which explains how this theorem works. So here is the graph. So we have two slice spectral sequence. The first one is a C4 spectral sequence. The second one is the quotient, a C2 spectral sequence. As you can see, the region above the slope 1, well, the region between slope 1 and slope 3 in the first sequence is the same as the region between slope 0 and slope 1 if you rescale the D3 in the second picture into D5 in the first picture. You can see the two regions are completely the same. So if you want to compute the slice spectral sequence when the group is large, you can apply induction. In this example, if you want to compute the C4 slice spectral sequence, since the C2 story already tells you what happens above slope 1, you only need to figure out the region between slope 0 and slope 1, which are these two regions. And here is a more abstract graph about how the slice recovery theorem works in general. So in general, when the group is C2 to the n, you can cut each of the cones into different regions, and they can be recovered by different localized slice spectral sequence on the positive cone, as you can see from tilde EFC2, which is the same as tilde EF1 and tilde EF2, and so on. On the negative cone, they are recovered by the mapping spectrum from different choices of tilde EF from different families. The transchromatic isomorphism can be explained by this graph. Since our slice spectral sequence computes the modular E series, so as you can see, if you check the slice spectral sequence on one such spectra, then different regions represents different data, I mean the data of different modular E series, together with their fixed points. So one way to study different regions in the slice spectral sequence is to apply the Tate spectral sequence. In fact, there are lots of structures which are hidden behind the slice spectral sequence, and we can use the Tate to detect them. So recall that when we construct the cogeometric and also the localized slice towers, we apply the top right element in the Tate in the Tate diagram, and also take the vertical fiber, which means we have a co-fiber sequence among the towers, which implies the following sequence among different spectral sequences. You will have a sequence from the cogeometric spectral sequence to the localized spectral sequence, and then to the Tate spectral sequence. In other words, since both cogeometric spectral sequence and also the localized slice spectral sequence detects different cones in the slice spectral sequence, so you may expect the Tate spectral sequence can detect both cones and also set up relations between them. And one advantage to use the Tate is the structures in the Tate spectral sequence are quite nice. I'm going to explain how the Tate detects different regions in the slice first. In the positive cone, we consider the usual Tate square of slice towers. As you can see, if you go rightward and then downward, you will have a map from the slice to the Tate. And we can prove that this composition, so from this map and this map, it induces an isomorphism between spectral sequences. Well, in the region between a line with slope 2 to the I minus 1 and a line of slope 2 to the I plus 1 minus 1, so it is a small conial regions. On the negative cone, you can find another map instead. You consider this larger graph, so it is the generalized Tate diagram together with its fiber. Since there's a map from the Tate, the bottom right corner, to the top right corner, the fiber of the map. So composing this map GI, together with this equivalence, together with this FI, the downward map, it will induce an isomorphism from the Tate spectral sequence to the slice spectral sequence on the negative cone, well between the line of slope 2 to the I minus 1 and the line of slope 2 to the I plus 1 minus 1. So here is one small degree shift. Since when you apply this fiber sequence, you will apply a desuspension on the Tate first. I'm going to show you one graph, and you will see how the relation comes from. So the left one is the slice spectral sequence of a special quotient BP module spectra. The right one is the Tate spectral sequence of the same spectrum. It is the F1 Tate spectral sequence. As you can see, if you focus on the region between slope 1 and slope 3, so the two red lines here, there will be isomorphism between the two regions bounded by these two lines. You can see the patterns here agrees with the patterns here, and also the patterns on the negative cone. So after a small degree shifting by 1 agrees with the patterns here in the Tate spectral sequence. And here is another graph. If you replace F1 by F0, now the isomorphism region becomes the region between slope 0 and slope 1. You can see we still have in both cones, these two regions are isomorphic to these two regions in the Tate spectral sequence. And here is a more abstract graph about how this whole theory works. The top one is the slice spectral sequence. The bottom one is the sequence from the cogeometric spectral sequence to the localized slice spectral sequence to the Tate spectral sequence. And here are maps which are induced by the generalized Tate diagram. This dashed arrow is the map when you take the D suspension and then you map to the fiber. So as you can see, I divide different regions with different colors, and the map induce isomorphism on the regions with the same color. So if you compare this composition from slice to localized slice and then to Tate, they will be isomorphic by this arrow from this region, the orange region in the positive cone between the line with slope 2 to the I minus 1 to the line with slope 2 to the I plus 1 minus 1 to the Tate in the corresponding region. Similarly, if you start from the Tate, you travel along this dashed arrow and then back to the slice, they will be isomorphic on the negative cone in the same region between the two lines. Well, in the Tate spectral sequence, you will see that there are several periodicities, and they will tell us that the information in the dual sectors, if you compare the orange region in the positive cone and the orange region on the negative cone, you will see the information they include will be essentially the same as each other. And here is the most important property of the Tate spectral sequence, which is also why we use that to detect the slice spectral sequence. Well, each of the Tate spectral sequence will have several periodicities. As an example, if you focus on G equals C4, in the F1 Tate spectral sequence, you will have several permanent cycles. Well, these are the expressions of the elements. You can see you have one cycle with order 1, 3, and another cycle with order 8 and 8. All of them will be killed by the longest differential in Tate, which is D5. In other words, these two cycles will imply two different periods in the Tate spectral sequence, along order 1, 3, and 8, 8. And here is a graph. So this graph is the F1 Tate spectral sequence. As you can see, there are two red arrows. The first one is the period with order 1, 3. The second one is another period with order 8, 8. Here's another example. If you replace F1 by F0, these are the elements which represents the period, which has degree 32, 0, and 8, 8. And again, they will be both killed by the longest differentials in Tate, which is D13, and hence induce periods. And this is another graph about how things works. As you can see, in this more complicated Tate graph, the horizontal arrow is the 32, 0 period, where this arrow is the 8, 8 period. And here is how we can describe the periods in Tate in a more concrete way. Well, roughly speaking, in general, when G equals C2 to the N, then in the Tate spectral sequence, well, in the Fi Tate spectral sequence, you will have two periods along the lines with slope 2 to the I minus 1 and 2 to the I plus 1 minus 1, which is the same as how we divide the cones in the slice spectral sequence into different regions. If you go back to these graphs, you will see how this theorem works. So along the two lines. In the F0 Tate, you have two periodicities along the line with slope 0 and the line with slope 1. In the F1 Tate, you have two periodicities along the line with slope 1 and the line with slope 3. So 2 to the 1 minus 1 and 2 to the 2 minus 1. The periodicities in Tate can explain the symmetry between the two cones of the slice spectral sequence. Well, in general, we say that the two cones are symmetric since they contain essentially the same collection of data. Well, in the spectral sequence. And here is one abstract example. We can construct one of the two cones if we know everything on the other cone. So we are going to construct the negative cone from what we know on the positive cone. And here's a graph about how this computation works. So we can begin with the positive cone of the slice spectral sequence. We begin with any arbitrary region, the region between the lines with slope 2 to the I and 2 to the I plus 1. So the Tate detecting theorem tells us that this region, the green region here, is the same as the same region in the Tate spectral sequence. But since we know the Tate spectral sequence is periodic along two different directions, so as long as we know this region, we can always expand it to the whole Tate spectral sequence. Then we can use another detecting map from the Tate to the negative cone of the slice spectral sequence. So we can focus on this region and we can recover the corresponding region on the negative cone. So by using this method and choose different Tate spectral sequence, we can recover different regions on the negative cone. So this method can help us to obtain all classes and interior differentials, which means the differentials which are entirely contained inside the region. There are still some differentials which is outside this computation. There are some crossing differentials. Some differentials crosses the boundary. Those differentials can be detected. Well, they can be paired by this more complicated pullback square. It is some kinds of square between different Tate and also the mixed Tate diagrams. The two mixed Tate spectral sequence will detect the crossing differentials in both cones. So if you know one of them, you can apply this pullback diagram to study the other. So finally, I'm going to talk about the periodicity and the computations. So the periodicity in the Tate spectral sequence is quite powerful in the computation of slice spectral sequence. So first, if we observe the homotopy of these spectral types of spectra, their homotopy will be periodic. In fact, their period can be implied by the same period in the Tate spectral sequence, by the horizontal period in the F0 Tate. Well, when moving away from degree 0, you will see a clear relation. So this period can be observed directly from the Tate. But if you move close to 0, especially when one period passes the 0 degree, then the period on homotopy will provide some additional information compared to the Tate spectral sequence. And we can combine these two periodicities to greatly simplify, or even finish the whole computation of the slice spectral sequence. I'm going to firstly explain how the two periods are related, the period on the homotopy and the period on the Tate spectral sequence. So here is the idea. Well, the rough idea is each differentials in Tate spectral sequence which crosses the horizontal axis will correspond to a pair of points which belong to which are the same as each other in the homotopy after several periods. So here is the graph. So whenever you have a crossing differential in Tate, crossing the horizontal line, since you can always move the top line by several periods to make it inside the region of the positive cone between slope 0 and slope 1, it will correspond to a point on the positive cone in the positive cone of the slice spectral sequence. Similarly, you can travel along several periods to pass the source in the corresponding region of the negative cone, which again represents the same class in the slice spectral sequence. The 2 points here will be the same as each other in homotopy after several periods. And here is also one reason why the horizontal period in Tate agrees with the period in the homotopy of the spectrum. Now I'm going to show you one example. So here is what we have. Well, it is an example about the computation of this slice spectral sequence of D inverse BP_C41, which detects the C4 fixed point of the model E theory E2. Before our computation, I'm going to explain this graph a little bit. So this graph only contains all differentials starting page 4, because there are too many D3 in the slice spectral sequence, which will cover the whole graph, but they are not hard to compute. So when we compute this spectral sequence, the the main challenging is to compute these differentials with length larger or equal to 5. Here, the red point and the black point denotes one copy of z over 2, where the white circle, the white point, denotes a copy of z over 4. The white box denotes a copy of z. So here's all the classes in this graph. So there are several tools we can use to compute this slice spectral sequence. Well, in general, when we compute a general spectral sequence, we can apply some degree arguments. We can apply the Leibniz rule if the spectra is a ring spectra. Since now we are computing a slice spectral sequence, there are also some. We can also use the transchromatic isomorphism, which tells us what happens above the line with slope 1, and we have two different periodicities, one from the Tate spectral sequence and one from the homotopy of the spectrum. Since there are lots of structures in this spectral sequence, so in practice, we do not need to compute all these differentials explicitly. Usually, after we compute some of them in an explicit way, we can use these structures to determine all the rest. All the rest differentials. So a natural question we may ask is, how many differentials we will need to generate everything in this graph? Well, the idea is we compute some of the differentials by tracing the classes, by computing it from the eCHT page explicitly. Then we apply the structure to generate everything else. The answer of this question is surprisingly small, since the answer is 1. So you have seen there are several strong structures in the slice spectral sequence. So now I'm going to tell you how strong they are. In fact, you only need to compute one differential in an explicit way. So you trace the eCHT page, you know it is a homotopy of HZ. You trace which class it is, and you compute the target of the corresponding differentials. Then you can throw away all the data on these differentials. You only apply the structures, and you can generate everything else. And here is the differential. Here is the only differentials you need to compute explicitly. So the red arrow here. I'm going to explain how this computation works. So first, starting from this differential, you can obtain two more differentials with the same length by applying the Leibniz rules after multiplying with these two elements which survive to the infinity page. So you obtain the two green arrows here. So before we continue, I want to recheck the periodicities we have. So first, in the Tate spectral sequence, in the F0 Tate spectral sequence, we have the period of 32, 0 and 8, 8, which implies the 32 period in homotopy. But in fact, if you consider only the E6 page of the Tate spectral sequence, you can halve these periods. You can show that you will have the 13, 0 and 4, 4 periods only on this page. Well, when the page becomes larger, you have to increase the periods to these final periods. So now we can continue our computation. As you have seen, we have 3 different D5 here. We can apply the periods on E6 together with our transchromatic isomorphism to obtain more D5. And here's what you will get. Starting from these 3 differentials, we apply the transchromatic to obtain everything above slope 1, and we apply these 2 periods on the E6 page of the Tate spectral sequence to obtain this additional D5. You can see as you travel along the top right direction, you just use the period 4, 4. And you can also travel horizontally by a period 16 and 0. So this tells us some additional D5, where they may or may not be all the D5. And then we can apply the periods in the homotopy. So first we begin with the gap here. So it is the gap theorem by HHR. As you can see, on the degrees -1 and -2 and -3, there are no classes here. Well, on degree 0, you only have one copy of Z. Since the homotopy has a 32 period, so if you move one period rightward, which means if you consider the columns, starting from 32 to 31, 30, and 29. All the classes will die except for this copy of Z. So they will not survive to the infinity page, which means we have to pair the additional classes here. You have 1 point here, 1 point here, 1 point here, and so on. We have to kill them by some differentials. And then you can apply some degree reasons. And here is the only answer. So you must relate this point to this point and send this point to this point. Along this column, you can see there are three different there are 3 points as sources and 3 points as targets. Here is the only way to match them. The reason is we already know that the Tate spectral sequence vanishes after D13, which means D13 is the longest differential in the slice spectral sequence. So we cannot have crossing differentials because its length will be larger than 13. So we have one D7, another D7, and also the third D7 here. So now we finish everything over these 4 columns from 29 to 32. Then we can continue and move forward. You can compare the column 28 together with the column -4. So after 132 period, you can see there's only one copy of Z over 2 which will survive to the infinity page, which means the homotopy is Z over 2. But here you have 3 leftovers. You have 3 points, 3 copies of Z over 2. Well, it is Z over 4 and killed by 1 copy of Z over 2, so you have Z over 2 left. Since you have the period on homotopy, which means only one of the 3 points can survive to the infinity page. But no matter which one survives, that point will be paired with the point on column -4. So they will correspond to one differential in the Tate spectral sequence. So the 3 point, if they survive, they will correspond to one D5, D13, or D21 in the Tate spectral sequence. But we already know that D21 is too long. The longest one is D13. D5 this point, the bottom point cannot survive because we cannot have a D5 here, since we can apply the 4-4 period. If this point survives, there will be a D5 in Tate. After the 4-4 period, it will be a D5 from this point to this point, which does not exist, because we already know this point is killed by these 2 differentials. In other words, the only choice is D13, and we can only have the middle point surviving to the infinity page. We can apply the same argument and keep pushing forward until we finish everything up to column 25. As you can see, we have some more arrows and we have some surviving points. I have used different colors to label the surviving points and also their paired point after a period of 32 here. So now after this computation, we can apply the 8-8 and the 32-0 periods. They will tell us everything else in the slice spectral sequence. So if you trace the whole story, we begin with one single computation on this D5, then we apply different structures on the slice spectral sequence, and then we obtain everything else. So here you can see how powerful this tool is by combining different structures. We are also trying to compute more slice spectral sequence with these techniques, and hopefully we can get interesting results from them. I guess that's all I want to talk about. Thank you very much.